So we are going to look at, I'm going to break this up over 2 days because the problems can take a considerable amount of time. I will tell you this, when we get to test day, right before the test, I will tell you whether it's a collision or an explosion, because I don't expect you to do both on the test. I think that's a little unfair. If you can do one, you can do the other. But I'm not going to tell you until the day before. There are 2D collisions and there are 2D explosions. I will randomly select one of those two to be on the test, and I'll just tell you the night before. Okay, so you need to be able to do both of them, but I'm only going to give you one, and I'll just tell you the night before. Be fair? I think that's fair. Okay. Yeah, waiting for Wednesday, right? And we're looking good because all I really got to do is this. So like today and tomorrow, I'll do collisions today. I'll do explosions tomorrow. Monday, Tuesday. I got your labs. I haven't marked them. I've been kind of busy. I'll probably get them over the weekend. I'll get it all back to you on Monday, and then on Monday and Tuesday, and we're going to wrap up test Wednesday, and we'll do the financial stuff Thursday, and then I can get You do on Friday. You do. So, Brett, great segue. Curling anyone? Now, what I'm about to show you, if you've ever curled before, this is the lamest video that I will show you. Have you seen this?
Yeah, you showed us last year.
I showed it to you last year?
I think so.
Okay, well, so you would think, I thought to myself a couple years ago, you know what? I should probably find a video about curling and physics. Surely in our large country of Canada, or even maybe somewhere in Europe, there's some physics teacher that's used curling to teach physics. Well, there is. He just happens to be at Santa Clara University in California, that hotbed for curling. So what you're going to see is A, some lame-o curling, and B, some lame-o acting.
The hotbed for curling.
Is physics a part of curling? Yes, of course it is. And all that bit about the sliding and the friction, all that is true. In fact, if you take a glass, I usually try to have a glass here. I don't know if this will work or not. If I spin it,
Everybody else tried it.
it might. I haven't practiced this, Brett, for a long time. Oh, that's a pretty good idea, Mervin. Man, that Mervin's smart, eh? If I spin it this way, whoa, which way did it go? The opposite way. Come over here.
Straight.
He didn't go straight. Watch how it finishes. Like if this was if this was ice and I spun it this way, it would go that way, right?
Whoa.
Which way did it go? Like the opposite way. So that's opposite curling, which is what they were saying. But we all know that when rocks hit one another, they collide and they move off. There is a little bit of friction, there's a little bit of energy lost, but they do tend to have conservation of momentum. Okay, so that's the idea. We're going to do exactly what we've done before, except now we're going to do it in 2 dimensions, which means we're going to separate it into X and Y components. In fact, you probably have all of the tools to do this already. But I'll remind you. Do you have this one right here? Okay, I'm going to go get my notes because I always screw this up. Okay, so 2 identical curling stones. Now, did you know, Brett, do you and Johnny know this, that all stones are not identical?
Yeah,
Did you know that? Yes, they're not, right? Which is why they pair them, they match them at major events, right?
Yeah.
To try to make them as identical as possible.
Now, what is a 1 and a 1 and a 2 and a 2? Like, that's what we're talking about?
Yeah, like the 2 lead stones, there is not a specific weight for it. You would think that they would, like a football has to be like a certain size. Curling stones can vary slightly. There's actually I know it's very weird.
Much more skill involved than these, yeah.
Absolutely. But for our purposes, we're going to assume that the mass is always the same. In this particular case, they are 19.5 kilograms. Okay? So we got 2 identical curling stones of mass 19.5 kilograms. They collide as shown. The first stone hits the stationary second stone with a velocity of 5 meters per second north. If the velocity of the first stone is 3.2 meters per second at north 30 west after collision, find the velocity of the second stone after the collision. Omit friction. So we're going to leave out friction for this time being here. Now, what happens what works best for me is if I do two different colors, you're going to have to go like A and B or something like that, right? Or do you want me to go 1 and 2?
A and B is cool.
A and B? Okay, that's too bad because my notes are 1 and 2, but I'll deal with it. Okay, so we've got a red one here, as I draw it in black. Let's go blue. Let's go curling stone A, and B is slightly offset. And a lot smaller. Thank you, Brett, for noticing, making me feel bad.
Very, right? That's good.
Now we're getting busy.
Okay, so after the first stone hits the north 30 west, so the blue one goes north 30 west, right? So A goes like this, which means that the red one's going to go kind of like that, right? We just don't know the angle. But we need to find the velocity. We're looking for VB after. When I say VB, I mean speed and direction. Okay, now here's where it gets crazy. Now I'm going to start with our old friend. Initial momentum is equal to final momentum. That's our framework. Right? No, you don't get a mark for that. But you should start with that. Now that means that all of the x components have to add up to all of the x components after, and all of the y components before have to add up to all the y components after. And I think I've done it opposite order. But anyways. Okay. Now let me just sort of gather my thoughts here. Oh yeah, now I remember. We're going to do this by vector subtraction. Because we realize that to begin with, only A is moving, right? Mm-hmm. So what is the initial momentum? That would be momentum of A, right? There is no B.
What?
Because B is at rest. Final momentum would be momentum A prime plus momentum of B prime, right? Prime means after collision. Now, what are we solving for here, EJ? We're solving for VB. I guess that's actually VB prime, right? And VB prime is part of this. So if I can get PB prime, I can get to VB prime. Okay, so solve this for PB prime. Well, why did I go red? PB prime, the PA prime goes to the other side, and you've got PA minus PA prime. And those are, of course, both vectors. So we just sort of turned this into a
Vector
subtraction question. You now have all the skills to do this, because you can do vector subtraction. Don't you? I mean, it's been a while. I'll give you that. It's been a while. But let's stop and think about this. How do I subtract vectors? I take them, I break them into components, and I just subtract, right? We can do this. I'm putting the notes down.
I don't know.
I'm feeling good. You know what? I was counting on you guys to make my day turn better.
Okay, let's go.
Okay, so let's take PA and let's draw that vector, right? So PA, and PA is just straight north, isn't it, right? Or straight up.
Yeah.
For the purposes of this, is it okay to superimpose north, south, east, and west on this?
Yeah.
I think so, right? And in fact, that's how they give us, north 30 west. So they give us that, right? Okay, so they made it simple. So PA, now remember we like our x's in one column and our y's in the other, and for whatever reason we like our x's first. So PAX is actually 0, right?
Yeah, it's only going up.
It's only going up, right? PAY. Oh, now we haven't actually done any momentum yet, have we? So that's going to be mass times velocity, right? So that's going to be the mass of A, which was 19.5, times the velocity, which I think was 5, am I right? Yes, 5 meters per second north. So 19.5 times 5. 97.5, right? 97.5. And that's going to be kilogram meters per second, I guess. Should I include units, or is that just going to clutter things up?
Clutter.
You want to include them?
Do we have to include them in the test?
Well, aren't they all the same?
They're all good. It's all going to be the same unit, right? I'm thinking, just for the sake of cleaning, keeping it clean, good curling analogy. Let's leave the units off. Until you're behind, then you'll throw as much junk as you can on the ace, right, Brett? At Johnny. Okay. So now what? Now I got to find out what PA prime is. So PA prime, this is A prime here, right? This thing here, right? So let's redraw this.
What?
Let's redraw that down here. And I realize you can't do that.
Oh. Yeah, I won't do that.
Right? So that's going to be PA prime X, and that's going to be PA Y, or PA prime Y. Oh, I'll tell you, if you were in grade 11, your head would explode. Like a 2D collision. Or explosion, I guess. So, PAX prime. X is opposite, right? So that is sine. But I haven't figured out what PA is. So it's actually mass times velocity times the sine, right? Right? So that's going to again be 19.5. The velocity of that now is 3.2. So that's just finding the momentum. 19.5 times 3.2. Tough to write with an eraser. Opposite sine 30. Am I right? Hey. Where are we taking? 19.5 times 3.2 times 30 sine equals, I get 31.2. Now, that x is to the,
Right.
do I need to include negative?
Yes, you do.
I sure do. I sure do. You have to be very careful with things here, right? Slow down, double check, think.
Slow down. Wait, where'd you get the 3.2? Slow down.
Because
Velocity.
the velocity is 3.2, right?
Got it.
Now, there's all kinds of different ways you could do this. Could we have figured out the momentum ahead of time and then put that number 31 point, and then multiply that by sine 30? Yes, there's lots of different ways to sort of organize your work. PAY prime then is going to be 19.5 times 3.2 times the cosine of 30. Why? Adjacent. Right? Adjacent. 19.5 times 3.2 times 30 cos. 54. And that is up. So positive 54.
No, that's all.
54.0, I guess, Josh. Josh, you don't have your earbud, do you? Oh, I'm sorry, yeah. I saw it there underneath your head, I couldn't see. Sorry. Okay, so now let's go back. PB prime is PA minus PA prime. So I have to take this one and subtract, right? I'm subtracting those. Am I right?
Sure.
See that? Right there, right? There's a subtraction right there.
Mm-hmm.
Okay, so this says that, so this means that PBX prime, the x component is equal to that one minus that one. So that's going to be 0 minus 31.2, which is 31.2, which isn't too surprising,
Oh,
right?
yeah.
0 minus 31.2.
Times because it's in the bracket.
Yeah, which isn't too surprising because the x component here has to match the x component there, right? Because the total x has to add up to 0, does it not? So in other words, they have to be the same.
Oh,
Yeah, now you're still, I can tell by the look, you're not sure.
that's what we just
It has to be the
So you know
same.
what?
No, just keep going.
That's negative, right?
That, the value of this one here is positive because it's 0 minus 31.2.
Oh, okay. Never.
The x component of b to the right is positive. Now, is it always going to be like that?
No.
Well, that's only true because this rock is moving straight north, right? So that means that the x component before was 0, so that means the x component after has to also be 0, right? So they add up together. Okay, so now P, B, Y prime, right? P, B, Y prime is what I'm solving for. And that's going to be this value here, 97.5, subtract 54.0.
Where?
Oh, is that a 2?
No, that's 31.2.
Did I get a good mark?
Stay with me here, Johnny. It's a whole lot easier if you listen and write at the same time. It's one reason why I repeat things, too, to give people a chance to sort of stay caught up. It's an old trick they teach you back in teacher school.
Teachers.
Do you repeat something after you say it?
2 or 3 times to give kids a chance to sort of process it and to re-emphasize it and all that stuff. So I'm going to go 97.5 minus 54. See how I repeated it again there? 43.5. And then I say what I'm writing, 43.5. The y component of b is 43.5. That's this y component right here.
Wait, what is that?
That's the y component of b's momentum.
Okay.
Right? Now, we're trying to get to the velocity for b, so I gotta take those x and y's and do what now? After vector subtraction, you gotta put them back together, right? So, 31.2, yeah. 31.2 is the x, 43.5 is the y, and the overall resultant is PB prime. It should be positive because it's to the right. PB prime is positive 31.2. So PB prime squared is equal to 31.2 squared plus 43.5 squared. PB then is going to be, we're going to square this out.
I'm just tired. I need rest.
Just as long as this is the last one, let me go.
53.5. I'm only doing this one question. Oh, hang on, maybe that's not entirely. 53.5. 53.5, and that is kilogram meters per second. I'm going to put that unit here now because I know that the next step is to break it down into velocity.
So we're not done yet.
Not yet. That is the momentum of B. Right?
Yep.
Okay, but how do I get the velocity of B?
PB, I mean P.
We are going to do the angle right away.
PI.
And it doesn't matter what order you do. P is equal to mv,
Wait.
Ah.
right? P is equal to mv. The momentum of rock B after collision is 53.5. The mass of rock B is 19.5. Divide to solve for the velocity.
Now we need the angle.
2.7. Does that seem like a reasonable value, 2.7 meters per second?
Yes.
The original was 5, the other one was 3.2. 2.7 is definitely in the right ballpark. Do we need the angle? I hear everyone yelling about the angle. Absolutely.
Good thing.
Inverse tan, opposite, adjacent, 43.5. Divide by 31.2. Second function tan, 54 degrees. So that's going to be, let me think here, east 54 north. Does that seem reasonable? I think so, right?
I totally forgot.
30 degrees, 54.
I totally thought this was about a curling round.
Now, your angles, in this case, your angles should be relatively close to 90 degrees. The standard sort of rule is that they should actually create a right angle, but because of friction, because of some energy loss, they're not always going to. Okay, but it should be relatively close to 90 degrees. Maybe I shouldn't even say that. Oh, am I done? Yeah, I think I'm done. Let me check my notes and see if I did it right. I really suck if I did.
I forgot this was about a curling
2.7 north, I got north 36 east.
Actually,
What did we get?
it's the exact.
North, is it the same? North 36 east.
Oh,
Yeah.
Same thing, right?
So you-
North 36 east,
How do you figure out that? Why do you do that? It's
There's some sort of flip.
because 90, yeah, it's just flip-flop, exactly.
Does that work? Oh, dude, that's just.
No, it just means that I drew this on my notes. I drew the 43.5 first, and then I went 31.2. That's all. I just drew it the other way. Okay, now is that not vector subtraction? Absolutely. So here's something for the exam. Because,
We're not doing vector subtraction twice in the exam.
well, if this question appears on the exam, you can use it for momentum, and you can go back to your vectors unit and say, hey, I did vector subtraction better on the exam, right? This is another example of vector subtraction. This question can be used for 2 questions, right, as a do-over.
Good job.
Oh, how much marks would this question be worth?
How much would that be worth? 1, 2,
That was a big mark.
3, 4, 5, 6, 7, 8. Yeah, probably 8 or 9.
Holy cow.
I like it, so you do.
Well, you don't even need that top part.
No, but it helps you to sort of just, right? Now, are there other ways to do this besides vector subtraction? Yeah, there are. I never showed vector subtraction until just a couple of years ago. I started to realize, oh, hey, this I can do it this way, right? And it sort of reinforces some old things.
Like all those P's.
I mean, yeah, it's just a visualizer. I think this is probably easier than the other way. I mean, you guys seem to get it, right?
What's the other way?
It's been so long I can't even quite remember how to do it. The other way.
Okay, never mind, we're good.
What are they teaching in universities?
I don't know.
Anyway goes?
Yeah, not sure. Probably depends on the prof. Okay, so that, my friends, that was a 2D. This one was actually what? This one was actually, oh my goodness, elastic, right? That one's elastic. This one here, you got a blue car and a red car smushing together. That's actually going to be inelastic.
Because they keep together.
You want to try for a minute, just sort of figure out how to do it? I'm going to give you 2 minutes to read it and think. This is inelastic. Take 2 minutes and think. Okay, how are we going to do this one here? Oh, that's not the right one. That's not the right one. Oh, you know what? I don't have answers to this one. Oh my God. What am I going to do? Yeah, that's one of the Simpsons where they steal the teacher's answers and never want to do.
No.
Oh, you guys, you're so uncultured. Don't know base space, don't watch The Simpsons.
I watched
What's wrong with kids these days?
Stop watching TV.
Family Guy and American Dad are better.
All right, let's work this out together. 2 1,000-kilogram cars are meeting at an intersection and about to collide. Car B blue is traveling at 20 meters per second east, and car R red is traveling at 10 meters per second north. Right away, I realized right angle, 90 degrees, Pythagoras. Awesome. And I also realized components, one's going to be, 1x is 0 and 1y is 0, right? So, sweet. After the crash, they stay together. What is their combined velocity after the collision? Okay, so let's write PI is equal to PF to frame our thinking.
1 mark
I'm
down.
not giving you a mark for that.
Why?
I'll give her half a mark. If we do it on the whole, a quarter of a mark.
What makes up the initial momentum? That would be PB plus PR, right? Momentum of the blue car plus the momentum of the red car. Now, are these vectors? They are. And what should we call the combination after?
What's blue and red mixed?
Purple, I guess.
PP.
I guess you could call it purple. You could call it like W for rec or C for combined, or you could even call it BR, C for crash,
Stop it.
P, BR.
Blue and red make purple.
Oh, let's go P purple. Now, if you were doing this, should you probably explain why you're calling it that?
No.
Why? We get marked.
Purple? No, you don't get a mark for
Why do
that.
you have to blue?
Well,
Why do you have to
I don't know, what the heck is that?
Blue and red make
Blue and red make purple, right? Okay, so is this going to be vector subtraction?
Yeah. No, it's.
I don't think so, because what are we solving for? We're solving for this, right? We're solving for the total. So this is not vector subtraction. You know why it's not vector subtraction? Because I'm already got this isolated. That's what I'm solving for. In the previous one, right, I was solving for that. I had to get that over to the other side. I had to do subtraction.
Oh.
Right? Okay, so this is now just vector addition. That's all it is, right? And not only that, but it's already broken into components, isn't it? In fact, do you have to do it by components? No, actually you don't. Could you? You could. But PB is simply what? PB is that. PR is? We're just going to do Pythagoras, I think, right?
Yes.
Why is this question easy?
This one is actually easier, right? So now we don't have our actual value. So maybe let's do this. So that's going to be 1,000 times. The blue one is traveling at 20. So that's going to be 20,000, right? And PR is also 1,000, and it's traveling at 10. So 10,000. So the blue one's going faster. It has more momentum, which means that the overall crash should be like, should that angle be 45 degrees?
No.
About 27 degrees.
It's 20, right? Right here,
I
20.
guess that angle.
No, can you just add them? They're vectors.
Yep.
They're vectors, Danielle. You got to add them by vectors. Right? Yes, you do get what that means.
The Y and the egg.
Right? It's going to be 20,000 here and 10,000 there, and this is P, I guess, right? PP squared is momentum purple squared, 20,000 squared plus 10,000 squared. So PP equals
Guys, only want one thing.
20,000 squared. Add them together, square root, 22,361. And that's going to be kilogram meters per second, right? That is a momentum.
I'm scared, Mr. Beck.
You're scared. Why?
Because I'm not going to do this right.
Well, pay attention now. I'm explaining it. So now what? Now I have to find the angle. It says find the combined velocity, right? So I have to do the same thing before. P equals mv. So 22,361. Oh, now what's the total mass after? 2,000, right?
The line clear.
1,000 plus 1,000. Yeah. So take that and divide by 2,000. 11 meters per second. Is that ballpark right?
Yeah.
11.2 actually, I guess. Well,
going?
One was going 20, the other was going 10. Larger mass, so it's going to slow it down a little bit. Yeah, that's ballpark, right? And what is the angle?
Yeah.
Football field right. Yeah, I don't know why ballpark is considered the word instead of soccer field.
Because if you're not in the right ballpark, you can't.
I guess. But what if you're like not in the USA where they don't play baseball?
Well, where's the origin of this phrase?
What?
What if you're not in the USA, like somewhere else where they don't play baseball?
I'm gonna bring baseball.
We're not gonna do it.
You're right. I know. I'm just saying someplace where.
Somewhere where there is no baseball.
Exactly. Thank you. 27 degrees. That's going to be east 27 north.
It's ruined by everything.
Also, the equivalent to north 63.
Yep. If you were an accident reconstructionist for the RCMP, you could then take that, figure out that you could probably measure. Now, an accident reconstructionist, would they be interested in the velocity of the right after? What the guy that figures out who's at fault?
They want to.
They want to know before, so they would likely do like the backwards analysis. How far did it go? What's the frictional coefficient? How fast is car B going? Are they speeding? Right? They'd be doing something like that. But that would be sort of after this.
Just doing one kind of thing.
Okay, I'll be quiet now. I did not.
Last night.
Who was it?
It was me.